Hello dear student, I am Dr. Avinash Ulle, Assistant Professor Sri R.R. Lauti Science College, Morshi. Today we are going to study the topic NMR spectroscopy. The phenomena of nuclear magnetic resonance, that is NMR, was first observed in 1946 and it has been routinely applied to organic chemistry since 1960. The subject has grown so fast that it has become one of the most useful methods for structure elucidation available to the organic chemist. Structure elucidation means the identification of unknown organic molecule or known organic molecules. In this technique, it is a nucleus of atom which undergo transition spin between two energy levels, and it is done by the absorption of radio frequency. The magnitude of this energy is very small, much smaller than the energy required for electronic transition, UV spectroscopy and vibrational transition, that is IR spectroscopy. This energy is available in the radio frequency radiation. Absorption of radio frequency radiation causes nuclear spin transition and signals appear. Means in NMR spectroscopy, basically the fundamental is that one nucleus which is NMR active will be discussed later. This nucleus spin about its own axis. At the same time, this rotation, the nucleus rotate in precession like a top, means it has two orientation, one along its own axis and one in a precessional motion. These two types of motion have the nucleus, and that's why this nucleus act as a tiny bar magnet. We know every charged particle, when it moves, it generates a magnetic moment. That's why this nucleus act like a tiny bar magnet, and when it absorbs the radio frequency in the presence of external magnetic field, it absorbs radio frequency, and the nucleus absorbs energy and goes to excited state, and when it returns from the excited state, it emits radiation or it emits energy, and that delta E recorded by the recorder, and we got a signal. That signal is called as a NMR spectrum, from which we are able to identify the unknown organic molecule by its structure. Introduction to NMR. It is a study of absorption of radio frequency radiation by nuclei in a magnetic field is called nuclear magnetic resonance. Earlier we discussed that the absorption of radio frequency by nuclei in a magnetic field, that study is called as NMR or nuclear magnetic resonance. Nuclear magnetic resonance spectroscopy is basically another form of absorption spectrometry. It involves change of the spin state of nucleus. Here one thing we have to notice, change of the spin means when this nucleus placed in external magnetic field, this nucleus is aligned with the external magnetic field, and some nucleus oppose the external magnetic field, but those in alignment with the external magnetic field have the lower energy, and they are situated at a ground state, and that nucleus absorbs the radio frequency and goes to excited state. Means when it goes from ground state to excited state, there is a change of the spin of the nucleus. That's why this word is involved. It involves change of the spin state of nucleus. When the nucleus absorbs electromagnetic radiation in a strong magnetic field, means this phenomena observed when we put nucleus in an external magnetic field, otherwise it can't show the NMR. The source of energy in NMR is radio waves, which have a long wavelength and thus low energy frequency. Means the frequency, radio waves are the very weak electromagnetic radiations, right? That's why they have the long wavelength and lower in energy or frequency. When low energy radio waves interact with a molecule, they can change the nuclear spins of some elements having spin state half, including 1H and C13. This spin state of proton and carbon is always half, in case of 1H and C13. Types of NMR. Two common types of NMR spectroscopy are used to characterize organic structures. Generally, there are a number of types of NMR spectroscopy, but generally we are use 1H NMR and C13 NMR. In 1H NMR, used to determine the type and number of hydrogen atom in a molecule. Means when we are studying the NMR spectroscopy, that time we are able to identify the number of protons present in that molecule. We can able to identify, and from that we are able to elucidate the unknown compound structure. In C13, there is a nucleus, that is a carbon nucleus, which having a mass number 13. Its spin is half. Used to determine the type of carbon atoms in the molecule. Means in 1H NMR spectroscopy we are dealing with the nucleus of proton, and in C13 NMR spectroscopy we are dealing with the nucleus of the carbon. Proton NMR means 1H NMR. It is a technique which is based on the absorption of electromagnetic radiation, the radio frequency region 4 to 900 megahertz by nuclei of the atoms. Means 4 to 900 megahertz frequency, in between 4 to 900 megahertz frequency absorbed by the nuclei. There are different nuclei which are absorb the radio frequency in different region from 4 to 900 megahertz. That's why each proton or each nucleus which is NMR active shows a different values for absorption, and from that we can able to identify the different types of proton present in a molecule. It is used to study a wide variety of nuclei, that is 1H, N15, F19, C13, P31. These all are the mass numbers which are odd. That's why these are the NMR active nucleus. These all atoms have the NMR active nucleus, and that shows the NMR. The most common form of NMR is based on the hydrogen nucleus or proton. It can give information about the structure of any molecule containing hydrogen atoms. Origin of NMR phenomena. Nucleus act as a tiny bar magnet. We already discussed the principle of the NMR. In NMR, why we call nucleus act as a tiny bar magnet? Because this nucleus when revolving its around one axis, it has a two orientation, one along the axis and one in a precession. That's why this nucleus act like a tiny bar magnet. When a charged particle such as proton spins on its axis, it creates a magnetic field. Thus, the nucleus can be considered to be a tiny bar magnet. Spin quantum number of some common nuclei. Spin quantum number I is related the atomic and mass number of the nucleus. Where spin quantum number, these are the spin quantum number: half, C13 having the half, and 2H means this is a deuterium, isotopes of proton, it having a spin quantum number 1, and C12 it having a spin quantum number 0, I is equal to 0. Those show I is equal to 0, those nucleus are NMR inactive or not NMR active, but those nucleus which are half integer or integer, half integer means 1 by 2, 3 by 2, like an integer means 1, 2, 3, like that, means one of atomic mass or atomic number. From these two, one must be a odd. That time the nucleus is able to show the NMR spectroscopy. If it is 0, when it is 0, when its mass number and atomic number both are even, that time that nucleus cannot show the NMR spectroscopy like C12, because in carbon C12 it has a mass number 12 and atomic number 6, both are even. That's why the C12 not able to show the NMR spectroscopy, but C13 able to show the NMR spectroscopy. Why? Because C13 nucleus having the mass number atomic or atomic mass that is odd, means element with either. From all these we can make one statement, that is element with either odd mass or odd atomic number have the property of nuclear spin. If an external magnetic field is applied, the number of possible orientation calculated by 2i plus 1, means if the nuclei present in a external magnetic field, that time that nuclei have a possible orientation that can be calculated by 2i plus 1. In case of 1H NMR and C13, the value of this spin quantum number I is half. That's why hydrogen has a spin quantum number I is equal to half, and possible orientation is 2 multiplied by I, that is 1 by 2 plus 1 is equal to 2, means hydrogen nuclei have a 2 orientation, that is plus half and minus half. We already discussed this nucleus revolving around its own axis. In it has a 2 orientation, one is a along its own axis and one in a precessional motion. That this 2 orientation, one is plus precessional motion, it has it act like a tiny bar magnet. But when this nucleus place without magnetic field, means this is a degenerated state, means this nucleus without magnetic external magnetic field is I is equal to half. It is neither plus half or minus plus half. But when we put this nucleus in a external magnetic field, that is B0, that time this nuclei align with the external magnetic field and having the minimum energy. Having the minimum energy means the spin of that nuclei is aligned with the magnetic external magnetic field, and it I is equal to plus half or alpha. But when it absorb energy, it goes to excited state, that is I is equal to minus half, or that is a beta. Okay, or we can say those nuclei which are in a alignment with a external magnetic field that have a more stable and those have a low energy. Means if this is a plus half, means its direction with the external magnetic field, and these nuclei which are opposes the external magnetic field. Look at here. These are the nuclei. We consider these are the proton nuclei. In absence of magnetic external magnetic field, means no external magnetic field is applied, that time we can see here this nuclei oriented randomly. Like these all nuclei oriented randomly, but as soon as we put the external magnetic field, that time we can see here some of the nuclei are in a alignment with the external magnetic field. This is the external magnetic field, direction of external magnetic field, and nuclei we can clearly see here these are in a direction with the external magnetic field, but some nuclei opposes the external magnetic field, right? Means their spin is opposite to alignment nuclei which are in alignment with the external magnetic field, and these are which have a alignment with the external magnetic field which are most stable nuclei. The same diagram here I try to represent in a different way, and from that we can conclude some things. Normally these tiny bar magnets are randomly oriented in a space when we are not applied the external magnetic field. However, in the presence of magnetic field, means the external magnetic field B0, they are oriented with or against the applied magnetic field, means with or opposite to the external magnetic field. The energy difference between these two states is very small, that is 0.1 calorie. The angular momentum of the spinning charge can be described in terms of quantum number, that is 1, half, 1, 3 by 2, 5 by 2, means integer or half integer. If the spin I is equal to 0, no spin and hence no 1H NMR phenomena is observed, means nuclei must need to have a spin quantum number. It is a half integer or integer. If it is a 0, that time that nucleus never able to show the NMR phenomena or NMR spectroscopy, means the which nuclei those have the atomic number as well as mass number both are even, that nuclei are not in a state to show the NMR spectroscopy. This is NMR instrumentation. You can see here this is a sample tube, radio frequency transmitter, sweep generator, radio frequency amplifier, detector, audio amplifier, and this is a signal, that is an NMR signal which are shown on a monitor, right? This NMR sample tube we see here, these two are the magnets to which we can call external magnetic field. Now look, this sample holder having the sample, means organic molecule which having a protons or C13 carbon, any we are talking about 1H NMR spectroscopy, so we consider here the organic compound place which contains protons. So protons contains this molecule present in this tube. That time the nuclei present in that molecule of proton is present in external magnetic field, means the nuclei of that proton some are in a alignment with the external magnetic field and some are opposites. So we know that two orientation plus half and minus half. This sweep generator always trying to try to carry the external magnetic field, means to vary in a very small difference, because in NMR spectroscopy we must need to make constant out of radio frequency or external magnetic field. Means if we fix the external magnetic field, that time the radio frequency we already told 4 to 900 megahertz, that radio frequency is always passing through this sample, and this external magnetic field is a constant. Otherwise you fix the radio frequency and vary the external magnetic field, but it need to put constant either radio frequency or external magnetic field to get the NMR signal. When this radio frequency is absorbed by this nuclei in presence of this external magnetic field, it get excited and it get flip if in a alignment with this external magnetic field. When it absorbs a radio frequency, it goes against the external magnetic field, and that flip is called as flipping. Means it excites, and but when it returns to ground state, it emit a energy, that is delta E, which is recorded by the recorder and sent to detector, and that detector amplify that signal and gives us a NMR spectrum. This is a short NMR instrumentation, and this type of NMR signal we can observe on spectrum. The NMR spectrum is plot of intensity of NMR signals versus magnetic field in reference to TMS. When we go to spectrum in NMR spectroscopy, this spectrum in start as a peak, that is of TMS, tetramethylselene. This is a standard reference sample considered for the NMR spectroscopy, by which we can able to identify the different proton signals at different place. When we look at the spectrum, we always calculate these signals value in del or ppm. At the right hand side we call upfield region, and to the left hand side we call downfield region. The solvent used in NMR. The following solvents are randomly used, in which hydrogen replaced by deuterium, that is CCl4 carbon tetrachloride, CS2 carbon disulfide, CdCl3 deuteriochloroform, or hexadeuteriobenzene or deuterium oxide. Means any organic molecule can soluble in these solvents which are listed here, and that solution filled in the sample tube, and this sample is ready for NMR spectrum. Chemical shift. A chemical shift is defined as the difference in part per million between the resonance frequency of the observed proton and tetramethylselene hydrogen. TMS is the most common reference compound in NMR. It is set at del 0 ppm. We already seen here the spectrum, that is, this is a TM used as a reference standard. From that reference standard we can calculate the number of different signals of a proton. That values are referred by taking a reference of tetramethylselene, and these values which are recorded, these are called as the chemical shift. If it is nearer or it is at the right hand side, that protons are called as a shielded protons are the shielded nuclei, or which are at the left hand side, means the chemical shift increases, that protons are the deshielded protons or deshielded nuclei. Means in short, the NMR spectrum with respect to TMS is always calculated, and those signals we got on that particular values, those values are called as the chemical shift. Means a chemical shift is defined as the difference in part per million, because chemical shift always have a unit, that is ppm, part per million, between the resonance frequency of the observed proton, tetramethylsilane hydrogens. TMS is the most common reference compound in NMR. It is set at del equal to 0 ppm. Means the tetramethylsilane have the 12 protons which are present at chemical shift or del value of 0 ppm. Chemical shift calculated by the formula frequency of signal minus frequency of reference upon spectrometer frequency multiplied by 10 raised to power 6. Shielding of photon. High electron density around the nuclei shields the nucleus from the external magnetic field and the signals upfield in the NMR spectrum. Means high electron density around the nucleus means more electron density is present around the nucleus of proton. That time we can say that proton get shielded by the electrons, and we call that is a shielded proton or shielding of proton, and that protons gives the signal in NMR spectrum at upfield region. Means the shielded proton always we got at the right hand side. Deshielding of proton, lower electron density around the nucleus deshields the nucleus from the external magnetic field, and the signals are downfield in the NMR spectrum. Means those nuclei or those protons which are not shielded by the electrons, or we can say okay, those nuclei which are not shielded by the electrons, those are experience a maximum external field, but those are shielded, those are not able to experience the external magnetic field. That's why the downfield protons always look at the left hand side of the chemical shift. Left hand side means this is 0 is a TMS peak. Always we got a TMS peak, that is a reference standard peak at 0, and from 0 when we go to the left hand side, the chemical shift get increases. Means the electron density around the nucleus of proton get decreases. Means those protons we got at a higher chemical shift, we can say that protons are a deshielded proton or in a downfield region. The most common of NMR, the most common form of NMR is based on hydrogen nucleus or proton. It gives information about the structure of any molecule containing hydrogen atoms. Information from spectrum means which informations gives the spectrum about the molecule, that can check by some points. The number of signals. The number of signals gives us the information about how many kinds of proton present in a molecule. Look, if this is a molecule, this contains 6 protons, right? This is contain 4 proton. This contains 6. This contains 6, 8, 10 protons. Means this number of protons gives a one signal or a different signal, that can be depend on the environment of proton. If they are equivalent proton, they gives a one signal, but If these protons are different, then they are given two peaks or two signals in the NMR spectrum. Means equivalent proton are those protons in which we can say in a molecule a set of proton with identical electronic environment in a molecule are said to be equivalent proton. Means this proton and this proton have the same chemical environment because it attached to carbon, this also attached to the carbon, and no other chemical environment or electronic environment is different in these two type of protons. That's why we can say these two protons, these three and these three, we can say they are the identical protons, equivalent protons. Means we in our spectrum for this ethane we got a one signal. We got a one signal. Why? Because these six protons are the equivalent proton. Why? Because they have the same electronic environment. That's why it gives only one set. Means these six protons are an equivalent proton. In case of this second example, these two protons and these two protons have the same chemical environment. It attached to chloro, this also attached to chloro. So I highlighted here these two protons are the equivalent. That's why AA, I put them AA, labeling them as a and AY because they have a same chemical or electronic environment, and it also give a one set of proton. Means NMR spectrum, this dichloroethane gives a one signal of 4 proton. In this example, two types of protons available, but out of this, from this is a propane. In this propane, we can clearly see here these three protons and these three protons have the same chemical environment because it attached to carbon. This also attached to the same carbon. That's why these two two set have the same electronic as well as chemical environment. That's why this 6 proton gives a one signal because these three and these three we labeled as a AA, means these are the equivalent proton, but the B proton is not a equivalent proton to this. This is a these two protons are a non-equivalent proton related to this CS3 protons. That's why in this example we got two sets of proton. This AA is a one set and B is a another set. In this example we see here these CS3 protons have the same environment. That's why these 6 protons gives a one signal because they are the equivalent proton, and these 4 B protons have the same or equivalent chemical environment or electronic environments. That's why this gives another set of equivalent proton. Means two type of equivalent protons are here, one is a and another is a B. That's why we got a two set of proton. But when we're talking about this type of example, this is a chloroethane. When we look at chloroethane, we can need to understand whether these two proton which is attached to same carbon atom are equivalent or not. That time you have to do one thing, just replace one atom by Z and check its mirror image. If its mirror image look like this, Z goes to this side and this is a mirror image, means this is a mirror image, but this is a non-superimposable mirror image because we put this molecule on over this molecule, that is non-superimposable. Mirror image which is non-superimposable, we call such a type as a pair, as a enantiomeric pair. Such enantiomeric pair, if we observe that time, we can say these two protons are the equivalent protons. Means in chloroethane these two protons are the equivalent proton. Non-equivalent proton. In a molecule, a set of a proton with a different chemical or electronic environment in a molecule are said to be a equivalent proton. This is a exact opposite to the equivalent proton. Look here. Here these three, these two, and this one. Three set of proton are observed here. This is A type of proton, this is B, and this is C. Why these are the different protons? Because they every set this have a different chemical or electronic environment. That's why they are not identical with each other, and that's why they are the different. That's why we say non-equivalent protons. These three protons A, B and C set are the set of non-equivalent proton. In this case we can clearly see we got a three sets, means in NMR spectrum this molecule shows the three peaks for the three non-equivalent protons. Second example, here also this these two proton, they have a different chemical. One is attached to bromo, one is attached to chloro, means these two proton and these two proton not having the same chemical environment or electronic environment. That's why they are not a identical proton. That's why we label them. One is a and another is a B, two sets of non-equivalent protons A and B. In this example we see there is A, B, C, D, four types of proton. Now you see here on this carbon atom, these are two protons are present, but these are not identical. These are not identical protons. Why? Because their chemical environment or electronic environment are different. This proton having the CH3 chemical environment, and this proton having the proton environment, means the electronic environment of these two protons are different. That's why these two protons are not identical. That's why we label them as a different. C and D, means this molecule shows four signals for the four different non-equivalent proton A, B, C and D. In this example we see here, from here is a OH group where it having the proton. This proton have a totally different chemical or electronic environment rather than other these four protons. That's why this is a different non-equivalent proton related to these protons, and these two protons have the same electronic as well as chemical environment. That's why these two protons are the equivalent proton. Like this, it having a environment of chloro. That's why these two types of protons are identical, right? Means in this molecule we got a three signals, three non-equivalent proton signals in NMR spectrum. That's why we say this molecule have the three set of non-equivalent proton, that is A, B, B and C. The position of signal chemical sheet gives us the information about the chemical environment of each kind of proton. Each kind of proton that we already discussed. Point number 3. The intensities of this signal gives us the information about the relative number of protons associated with the signals. Means the intensities of the signal. If we consider this molecule, okay, this is a xylene. It having a two set of proton, that is this two CH3 proton, 6 proton have a same chemical environment. That's why these are the equivalent proton, and these two have the same chemical environment. That's why these two and these two 4 protons have the second set of equivalent proton. Means we need to show NMR spectrum for this molecule two sets of a signal of non-equivalent proton, one set of 6 equivalent protons and one set of 4 equivalent proton. Means these, we say this 4 proton as a set which contains of 4 proton, 4 hydrogens, and this B contains a 6 hydrogen. When we look at the NMR spectrum of this molecule, we how to calculate the number of NMRs from the signal intensity. Look at here. This is a TMS peak. This is a reference which is always present at 0. When we move to left side, here we got one signal. Its intensity is maximum. Its intensity is maximum related to this peak intensity. Means this intensity or height of this signal indicate that the number of protons are maximum at that position. At this position, when we draw this type curves and when we count it in a millimeter from this curve to this baseline, if we measure it, it comes 6 millimeter, and from this we measure the intensity or height of this peak, it comes 4 millimeter. From that we can calculate the number of protons present in that particular signal by integrating this signal. And 1 millimeter is equal to 1 proton. Here is a 6 millimeter. So this peak intensity indicates that this signal contains a 6 proton, that is 6 hydrogen, and this contains a 4 hydrogen. Means from the intensity of the signal we can able, or it gives the information about the relative number of proton associated with the signals. Number 4. Splitting of signals into several peaks gives us the information about the environment of protons with respect to other nearby proton. Take an example. We have taken an example of 1,1 dibromo 2 bromo ethane. Here we see in this structure this CH means, and this CH2, this proton and this proton are different by chemical environments. Means here in this molecule need to show two signals, one of this proton A and we say this is a B, means this molecule shows a two NMR signals. But when we observe a signal, that signal gets split. That signal get split when we're talking about particularly this proton, this tertiary proton, right? Signal of uncoupled proton. If this we're talking about this, it gives the information of adjacent carbon atom or a nearby. We can say the information about the protons, the environment of the protons, how many protons are present at the adjacent site of that particular proton. If we are talking about this proton, we see here this proton split into triplet 1, 2, 3. Why it is split in triplet? Because this proton coupled with this non-equivalent proton, and if it is a it have the two proton at the adjacent side, it's split into triplet. Why into triplet? Because this arrangement of these two nucleus is like this. Both nuclei against the magnetic field, both nuclei align with the magnetic field, or out of these two, one against the magnetic field, one with the magnetic field, or one with the magnetic field or against the magnetic field. Means we can say here we already got three signals because these are the similarity. That's why we eliminate one and we got a triplet like this. 3. Spin orientation of CH2 protons means the spin oriented in three ways: with magnetic field, oppose magnetic field, or with or oppose the magnetic field. That's why we can calculate the environment adjacent to the particular proton, which signal we can study it. Means we are talking about this proton. This proton gives, this tertiary proton gives a triplet, right? 1:2:1 ratio. 1:2:1 ratio. From where it calculated? 1:2:1 means how many arrangement of nuclear spin is possible. It can be This can be done by showing these peaks. Here we see 1 is to 2 is to 1. That's why this signal is splits into ratio. This ratio is 1 is to 2 is to 1, means from this splitting of signals into several peaks we get the information about the adjacent environment of proton, whether there is a presence of proton or not, or how many protons are present at the center. But when we're talking about these signals, the signal of these protons are split into doublet only. Why? Because to these two protons adjacent to this proton which have only one proton, and the adjustment of this proton is only in two possible orientation, with field or against the field, with field or against the field. That's why it can show doublet. That's why it can show doublet. Here we can clearly see this is a peak for CH proton. In NMR, this is a peak for this CH proton, which split into triplet. Why it split into triplet? Because it's adjacent. This proton have a two proton at the adjacent which are non-equivalent to related to this proton, and this two CH2 protons split into doublet because it having the environment of one proton. Okay, the next part we will see in the next lecture. Thank you.